Here we continue talking about electric potential. Here we have a uniform ring of charge with radius r and a charge per unit length of lambda. Recall that lambda is coulombs per meter. So if we wanted the total amount of charge around this ring, we would take lambda and multiply by the length or the circumference of that ring, which would be 2 pi times r. That will come into play later. Does the potential V at point P have magnitude and direction, or just magnitude? And the answer to that is that the potential at any point, not just here at P along the central axis of this ring, is a scalar. And so it just has magnitude. In some cases, it could be positive. In some cases, it could be negative. Here we know it's going to be positive because the charge that is responsible for creating that potential is positive. But if this were a negative lambda, then the potential at point P would be a negative number, but it definitely wouldn't have any direction. So we don't have to take sine or cosine or theta into account at all. So now let's determine the electric potential here at point P. To find the total potential, what we want to do is we want to add up all of the little potentials due to all the dq's that go around this loop. And in general, a potential due to a point charge is given by kq over r. So a dv is going to be k dq divided by r. Now what's r? R is the distance to there. And so r, if we want to change that denominator, it's going to be capital R squared plus h squared square rooted. Now what we notice is that for this specific case, that value of r is a constant for every bit of this ring. Every one of these little dq's has the same value of little r, which means this thing in the denominator, as well as k, can be pulled out of the integral, and we are left with, let's put on the front there, k over the square root of big R squared plus h squared. And now we need to then just integrate dq, which means we need the total amount of charge. The total amount of charge is going to be the charge per length, lambda, multiplied by the circumference of that ring. And so this term here is going to be nothing more than 2 pi big R times lambda. And if we put that all into one expression that looks nice, we get our final answer. 2 pi k r lambda in the numerator, and in the denominator, the square root of big R squared plus h squared. And that would be a positive number. It would have no direction. Now what we have is a couple of point charges, one positive, one negative. And what we want to show here is that close to the charge, there's a big value of potential right there. Further out, it's somewhat smaller, and further out yet, it's even smaller. And this trend occurs in every direction. To the left, to the right, above, below, even towards us and away from us. So what we end up with, and this is actually a story for another video, we're going to end up with basically an imaginary sphere around this charge, and each point on that sphere has the same value of potential. And then there's going to be another imaginary sphere further out. Each of those points will have the same value of potential, but that potential will be a smaller number than the potential associated with all of the points on an inner sphere, etc. We get the same sort of thing happening here with this negative charge. We have a large negative potential close, and as we get further away, the potential is still negative, but it gets smaller and smaller. And now we want to show which way a positive charge would be forced and which way a negative charge would be forced. Well, a positive charge would be forced in this direction, And a negative charge, as you know, would be attracted, wouldn't it, to that positive Q. And over here, a positive charge would be attracted to that negative Q, and a negative charge would run away from it. So in general, positive charges go from higher magnitudes of V towards lower, and that's also the case here, because this is negative little v getting a little bit bigger negative, even bigger negative, more positive to more negative values of potential. That's what positive charges do. And negative charges go from larger negative potentials toward more positive potentials. Let's finish with part 6 here. In moving a charge from here to there, the signs of the work done by the electric force on the charge and that of the change in potential energy depend on the sign of the charge and the direction of the electric field. So if we have a charge and we let go of it and whoop, there it goes, that's because the electric force is doing positive work. The force and the direction of movement are in the same direction. Similarly, if we have a charge and we have to push it ourselves to get there, the electric force is fighting us. And so when we move it, the electric force is going to be doing negative work. And so what does that mean? According to this equation that I'm going to write over here on the left, which we've seen before, the work done is equal to the opposite in change of potential energy. In this case, the potential energy will be negative, and in this case, the change in potential energy, I say, will be positive. Anytime, whoop, there it goes, the change in potential energy is negative. Anytime we have to push it to get there, the change in potential energy is positive.